Yeah, hi everyone. I can't believe we already completed the second week of this semester, but in the meantime, there have been a lot of interesting things happening in the deep learning and artificial intelligence world. So here I'm back with stuff in the news number 2, some of the interesting things that happened this week. So we will be mainly seeing things from my perspective, things I've been reading about, but I also had to trim down the list quite a bit because there are always lots of interesting research papers and news articles coming out. So, but with that, let me not waste too much time on the introduction and get started with the stuff in the news. Yeah, one of the things that piqued my interest this week was this article entitled "CMU Researchers Explore Crazy Idea of Automating AI Paper Reviews." So paper reviews, that's a very, I would say, sensitive topic in the deep learning and machine learning community right now, because at these top conferences where people submit papers like ICML and NeurIPS, there are usually around, 5 to 10,000, let's say 10,000 submissions every year nowadays, and it's pretty challenging to find or to maintain good quality reviews. I'm also a reviewer for both of these conferences and get about 3 to 5 papers to review. Also, the timeline is very short, and if you have 10,000 submissions, you have to find also 10,000 reviewers, every one of those reviewing 3 papers or more, and it's really hard to keep up with these numbers. So I think that was what motivated these people to work on this idea. I would say I'm not honestly convinced this is a good thing to work on or even try to automate paper reviews with AI. Maybe it's good for checking general formats like beyond the conventional quality checks, like whether the paper has a right page limit or right template and things like that. Maybe AI can be used for some quality checks. I'm a little bit skeptical whether it can be used to really should make decisions on the quality or regarding the quality of a paper. Nonetheless, I think this is an interesting project from a language perspective, like assessing how far deep learning has come in terms of understanding human language and contents of more comprehensive texts. And also what I found as a general interesting takeaway are these most frequently mentioned qualities of a good review. So these are things to assess whether a peer review is good or not. And this is actually something I'm thinking about adopting as a rubric for our class projects, because like I mentioned before, there will be a peer review for our class projects at the end of the semester, and I will of course share more details later on during the semester. But this might be a good rubric for me also to assess whether the peer reviews you write about the reports of other students might be good peer reviews. So something like decisiveness, comprehensiveness, justification, accuracy, and kindness. Kindness is also very important because reviews can sometimes be grumpy, and I think it's usually not very nice and not very fair to write grumpy reviews. All right, so this model they proposed is based on BERT and BART. BART is a denoising autoencoder. It's related to BERT. And this is for pre-training sequence-to-sequence models. We will talk more about sequence-to-sequence models in part 5 of this course at the end of the semester. So sequence-to-sequence means that the input to the model is a sequence and the output is also a sequence instead of just a single prediction. So instead of just predicting a single class label, you are outputting also a sequence. For example, text. A simple example also of sequence-to-sequence models would be, for example, language translation, where you translate from one language to the other. So here they involve, of course, human annotation. So they annotate the paper with these statistics. I think SUM stands for summary, or actually posted it here, summary. MOT is for motivation. SUB is for substance. So humans tag the article with these different aspects. Then they train a tagger that can do the same thing. Then there's some post-processing going on, and then a human has to evaluate the results. So if you are interested in this project or want to read more, there's the paper here on arXiv, and they also posted the code on GitHub. So if you want to play around with this, if you're curious. All right, moving on. You have probably never wondered what a night made of spaghetti would look like. So this is not new news. It's a little bit older. It's like a month old or something. There's like a machine learning project called DALL-E. It's like, I think, a mashup of Wall-E and the artist DALL-E. So in that way here, what the researchers did is they trained another language model, GPT-3, 12 billion parameter model. And in this DALL-E model here, which is based on GPT-3 or the concepts of GPT-3, what the researchers do is they train a model on images and descriptions of images. And then, so these are the inputs. So you can think of it as ImageNet, for example. And then you can query the model and it gives you outputs, and the outputs are mashups from the text input. So for example, you can type in spaghetti night or night made of spaghetti. You can type that in and the model will produce new images that have both concepts in common. For example, night and spaghetti. And here are some of the results of nights made out of spaghetti. So these are images that don't exist. This is something the model synthesized. Unfortunately, the paper is not available and the code is also not available, but there is a blog article if you want to read more about this project. I thought it might be also a fun project, especially if you're interested in generative models. And while the DALL-E paper and code are currently not available yet, one part of DALL-E is available, this so-called CLIP model or approach. So CLIP stands for Contrastive Language Image Pre-training. So this is something that DALL-E uses under the hood. It's also based on GPT-3, I think. So, and what CLIP does, you can think of it as almost like an image classifier in that sense, but it is doing something clever. So CLIP is based on zero-shot transfer. So here zero-shot means classifying something where you don't have any training example for. So as I mentioned earlier, I'm also working a lot in the area of few-shot learning with my student Zhongji. And in few-shot learning, we have this setting like n-shot k-way few-shot learning. So the n in n-shot few-shot learning stands for the number of examples per class, and k is the number of classes. So for example, if you have let's say a 5-shot 10-way few-shot learning problem, that means you have 10 different classes but only 5 examples per class. A very small problem, and it's very challenging to develop deep learning systems that can work with such small data sets. So zero-shot is even more extreme. It really means you have 0 examples. So in this case, the model should predict something even though it may have never seen this class before. So how would you approach this? So for that, the researchers use natural language supervision and multimodal learning. So multimodal learning stands for or means using different data sources. So here they use image data and text data. So that's where the natural language supervision part comes in. So in particular, they are predicting novel image classes based on word embeddings. So when they train the data set, the model, they use both descriptions of an image and the image itself, and then if they see a new class, they can use word embeddings or the descriptions to predict the class. So here's an example of that. So this is from the paper, or the blog post, I think, that I linked here. So what they do is here they compare their model with a regular residual net 101. This is something we will also talk about later in class. That's a convolutional network trained on, I think it's trained on ImageNet. And I should say none of this CLIP thing is fine-tuned to these data sets. So it's trained on a different data set and then applied to data sets it has not been fine-tuned to. So this ResNet here was trained on ImageNet and it reaches 76.2% accuracy, prediction accuracy. This CLIP model, which was trained on a different data set, also reaches 76.2% accuracy on this data set. But what's more impressive is it also achieves good performance on different types of ImageNets that were not contained in this training set. So in that way, this clip model generalizes better to other types of data sets by this concept of this contrastive language image pre-training. So that is also, I think, an interesting idea or approach, and you can also find more about this in the paper here, and the code is also available here. And this, I think, can be potentially really useful if, for example, you develop, for example, let's say a self-driving car, and you have a large data set and you want to look for specific videos or clips or different images. Like I want to have an image of, let's say, a pedestrian crossing a busy intersection. So in this way you can have maybe this model finding your query very efficiently in a large data set. And why is that interesting? Because you can imagine you don't have to train the model on all possible queries. If you have these word embeddings, you can search for something that is similar to your input word embedding, and it pulls out the corresponding image. So in that way, I think this is actually a very interesting approach. And here's a big picture overview of how the method works. It has been some time since lecture 1, where I think I briefly mentioned it, but contrastive pre-training, that's a form of self-supervised learning. And here in this particular case, what they do is they train a model on text descriptions and images. So in the example I gave earlier about self-supervised learning, the researchers used an image and then a transformed version of this image, and the model had to predict whether it's the same image or not compared to an image that is different. So like being able to distinguish different images from each other and modified versions of the same image. And here in this case, it's kind of a similar concept, but here it's based on text data and image data. So they train this text encoder on the text description and the image decoder on the image description. So they produce then a so-called embedding, and then based on the text and the image embedding, the model learns like the relationship. So it should be basically let's say I think that's what it means for the diagonal. If you have an image from a certain class, from this class, and a description that matches this class, it should give a high relationship score or something like that. So you would train the model basically to associate the right description with the right image. And then you can, if you have a data set of descriptions and images, you can shuffle them, and it should give you a low score if you have a description that does not match your image, and so forth. So let's say you pre-trained your model, then you can create a dataset classifier from text labels. So here what they do is they embed the class label in a text description. For example, here a photo of a plane, car, dog, bird, and so forth. And then you produce these text embeddings. And now imagine you have a new image that you want to classify. You don't know the class label, that is what you want to find out. So in this zero-shot prediction, this means this class label doesn't have to be in necessarily the training set. So you don't have to have an example of that if you have the right embeddings. So in that way, what they have here is they have this image, they give it to the image encoder, and then you have an embedding, and then you would pull out the text description embedding that has the highest score. So in this case, a photo of a dog, for example. So in this case, you, from the text encoding and the image, you would then pull out the class from that one. That is on a high level how this clip method works. I mentioned the model GPT multiple times, GPT-2 and GPT-3. Unfortunately, GPT-3 is not available yet. So this is a model by OpenAI. For GPT-2, I'm actually not sure whether it's already available. I haven't followed it very closely. However, I also saw now an initiative to train an open source version of that model. So here they say our primary goal is to replicate GPT-3 sized model or models and open source it to the public for free. So they train the models on the dataset called the Pile, which is a 825 gigabyte model, including like YouTube descriptions, papers from PubMed, and so forth. And it is like a 200 parameter model. It's very big. So it's a big initiative because these models for us normal people are really out of reach. You really need a big company to be able to train such a model. And I remember when the first BERT or GPT models came out, I think it was estimated the cost was estimated to be around $100,000 just to train the model. And I think for this GPT-3, which is magnitudes bigger, it's probably in the realm of almost $1 million to just train the model. So it's actually good then that someone maybe does that in a way that is then also available and free for the public. All right, so moving on. I also saw, it's not directly related to deep learning, but I also saw this news article today. So it's about the popularity of programming languages and tools. So this is by O'Reilly, and they base their analysis based on queries on their website and books and things like that, like mostly search terms on their website and what people look for. So unsurprisingly, Python is of course in the first place. Also, it's growing again, so it's still not stagnating. So people use more and more Python, which I think is good to know. So you know where things are headed. What I also found interesting is Scala. So Scala, I thought personally that might be the next hot thing when I was in grad school. When I was in grad school, everyone started talking about Scala at some point, which is a language kind of related to JavaScript, or I think it runs in the JVM, the JavaScript virtual machine. Personally, I have to say I never really used it, and now seeing that there's this big decline, I'm also glad that I didn't waste my time learning a new programming language, because that's also always a trade-off. It's like the trade-off between doing research, getting things done, and doing things like learning new languages. So there's like a trade-off. You want to always be up to date with current technology and what people are doing, because that's how you keep up to date and can produce cutting-edge work. But then also you don't want to waste your time by pursuing things that are maybe not worthwhile. So for now, it seems like Python is still a good choice for machine learning and deep learning. All right, so another interesting project I saw was this approach or method by Facebook AI Research, where they are teaching AI to manipulate objects using visual demos. So it's currently very challenging still to train robots. There's a field called reinforcement learning, as you recall from the introductory lectures. So in this way, robots learn by trial and error. So you train a robot to do something by having it fail a lot of times. And there's another approach to reinforcement learning called inverse reinforcement learning, which is like learning based on a demonstration. However, traditionally it was kind of also not very easy, because you had to have a virtual environment for that, where you can simulate this behavior that you want your agent to mimic. So here, Facebook AI Research proposed a model-based inverse reinforcement learning approach using visual demonstrations on a physical robot. So that means the robot can learn by looking at something on a video or series of images. Instead of having this virtual environment, for example, a video game context, a 3D world, you can show the robot images of a task that a human performs. For example, here a human is grabbing a bottle and moving a bottle around. If you show the reinforcement learning agent the video, it can to some extent learn to perform this behavior as well. So there's a video. I can't unfortunately play it in the slides, but if you're interested, you can find out more here under this blog post address, and there's also the code available on GitHub. Lastly, the last topic for today is about t-SNE, T-Distributed Stochastic Neighbor Embedding. And this is a very popular technique in deep learning to visualize high-dimensional data sets. So here I have an image of MNIST. So MNIST, as you know, is a high-dimensional data set, right? So for MNIST, for these handwritten digits, you have 28 times 28 pixels, which is 784 dimensions. So you have a very high dimensional data set, and you can't really easily visualize that in a scatterplot, for example. So you can use t-SNE though to reduce the dimensionality of this data set into down to 2 dimensions. And the interesting aspect about t-SNE is that it preserves the relationship between the high dimensional space, between the objects in the high dimensional space and in the new lower dimensional space. So here is the result of a t-SNE dimensionality reduction into 2 dimensions. Let's say you have 2 features now, x1 and x2. And you can see that the t-SNE algorithm takes these high dimensional 784 dimensional MNIST embeddings and puts them into this 2D space such that the relationship between the numbers is still preserved. You can see all the zeros here cluster together, all the sevens cluster together, all the fourths cluster together, and so forth. So you can see it kind of preserves the relationship, or the relative meaning of these numbers by when it is projecting those into a higher dimensional, lower dimensional space. And you can also think of it as principal component analysis, but principal component analysis is it's a linear transformation. So PCA is a linear transformation. And this method here, the t-SNE method, is not just a linear transformation. It's a little bit more involved than that. I actually taught t-SNE in Statistics 479. I have actually some slides I can upload. I had a full lecture on that. I don't want to go into too much detail here, but it's a very cool method. It's really useful. But one kind of downside of that is that you have to tune the hyperparameters in order to make it perform well. And usually you don't know, because you don't know the labels always, you don't know what a good setting is. So there was a paper I saw this week. It's about initialization is critical for preserving the global structure in both t-SNE and UMAP. So here the researchers say that it's really important that you choose the right parameters when you use t-SNE, the right hyperparameters, and one of those is the random start, like how you start t-SNE, the initialization. And here they found that t-SNE will perform much better if you use actually PCA as an initialization. You basically initialize t-SNE with PCA result. So in that way, they found that, for example, when they compared t-SNE with PCA initialization and the random initialization, that t-SNE performed much better across everything here, almost everything. I think the way they measured that, and if I recall correctly, is they measured the correlation between the distances in the original space and the reduced space. So if I go back, they would compute the distance between 2 images in the high dimensional space, and then they would compute it in the low dimensional space, in the 2-dimensional space, and then check the correlation for these different approaches. And they found basically that using t-SNE with PCA really preserves the distance between objects in the low dimensional space. Here, as you can see from the title, there's another method called UMAP. This is also a very good method, and it's recently even become more popular than t-SNE because sometimes it's even better at preserving this structure. So with that, this is t-SNE. I think you may probably want to use it at some point in your class projects. It's really useful for visualizing high-dimensional data sets, but in practice it's not really only used for visualizing data sets. It's usually also used for understanding what a deep neural network does. For example, you would apply that to an embedding of a neural network to really understand what information is contained in the network. So if you have a big convolution network, so you usually have layers that become smaller in size the deeper the network becomes, and then researchers, for example, would take the later embeddings and then apply t-SNE to see how well it separates different classes in this lower embedding and so forth. Just like a last thing here about t-SNE. So in scikit-learn, the initialization scheme is a random initialization. And here if you want to use t-SNE in practice, according to this research paper, you want to change that to PCA. So instead of using the default random, you would want to use PCA because it performs better according to this paper on the previous slide. And also there is a discussion right now on the scikit-learn issue tracker where it's proposed to change this default behavior so that it will also use PCA by default. And then also there are some other tips. So if you want to use t-SNE, I would recommend you to check out this issue here where there's a more in-depth discussion. And with that, I think it's already a long video, so enough news for this week. I will see you on Tuesday with the next lecture.